our own solar system and distant worlds orbiting remote stars, and to delve into the complex structures of our universe and the role we play in it. In a recent initiative, scientists directed the Webb telescope toward a star located at a distance of 120 light-years from our solar system. This time, the super telescope has revealed evidence for the existence of carbon-based molecules in the atmosphere of a possible ocean world outside our planet, which has baffled the astronomical community. How is this surprising revelation possible? This finding provides a fascinating glimpse of a planet that differs significantly from any other within our solar system and raises interesting questions about the possibility of potentially habitable worlds in other corners of the vast universe. Join us on this journey to discover more details about this exoplanet. If you're interested in keeping up to date with news about the universe and its surroundings, subscribe to our channel. Be sure to like this video, share it to reach more people, and turn on the notification bell. NASA's James Webb Space Telescope has made a relevant discovery regarding the exoplanet K2-18b, which has a mass 8.6 times that of Earth. This finding consists in the identification of the presence of carbon compounds such as methane and carbon dioxide in the atmosphere of this exoplanet. Webb's discovery adds to previous research suggesting that K2-18b may be a planet with characteristics conducive to life, as it appears to have a hydrogen-rich atmosphere and an ocean-covered surface. The first exploration of the atmospheric properties of this exoplanet in the habitable zone was carried out using NASA's Hubble Space Telescope, which transformed our understanding of this system. It is important to note this exoplanet is located at a distance of 120 light-years from Earth, located in the constellation Leo, orbiting a cool dwarf star called K2-18, which is within the habitable zone. These exoplanets, such as K2-18b, which are between the size of Earth and Neptune, are a rare category in our solar system due to the lack of similar planets in close proximity. The possibility that K2-18b is an exoplanet with a significant abundance of carbon and a hydrogen-rich atmosphere is intriguing to astronomers, as some experts believe that these worlds could offer ideal conditions for searching for signs of life on exoplanets. The presence of methane and carbon dioxide, along with the absence of ammonia, supports the theory this exoplanet could harbor an ocean beneath a hydrogen-rich atmosphere. Early discoveries regarding that exoplanet also raised the possibility of detecting a chemical called dimethyl sulfide. This compound is generated only by life on Earth, with most of the dimethyl sulfide present in the atmosphere resulting from phytoplankton activity in marine environments. However, the interference of presence of dimethyl sulfide in the atmosphere of K2-18b is less robust and requires further confirmation. Further observations from the telescope network should be able to verify whether dimethyl sulfur is present in K2-18b's atmosphere at significant levels. An astronomer at the University of Cambridge explained, although K2-18b is in the habitable zone and has been shown to contain carbon compounds, this does not automatically imply that the planet is capable of harboring life. The fact that it has a radius 2.6 times that of Earth suggests that its core is probably surrounded by an immense high-pressure mantle of ice, similar to that of Neptune. It also possesses a thinner hydrogen-rich atmosphere, along with an ocean-covered surface. Although oceans of liquid water are expected on this exoplanet, there is a possibility that the ocean is too rigid or inadequate to support life. However, the researchers have managed to obtain the most detailed spectrum to date of a habitable sub-Neptune, which has allowed them to identify the molecules present in its atmosphere. A member of the Cardiff University team explained, this challenge was met by analyzing the light coming from K2-18b's host star as it passed through the exoplanet's own atmosphere. K2-18b is what is known as a transiting exoplanet, meaning that its brightness decreases as it passes in front of its host star. In fact, this is how NASA's K2 mission was able to detect this exoplanet. This approach implies that a small portion of sunlight passes through the atmosphere of exoplanets before reaching space telescopes such as the Webb telescope. During these transits, when sunlight passes through an exoplanet's atmosphere, it leaves traces or signals that astronomers can gather to estimate the gases present in that atmosphere. The research team plans to conduct further investigations using the telescope's mid-infrared spectrograph, which will confirm their findings and provide new information about the climatic conditions on K2-18b. Their ultimate goal is to search for signs of life on habitable exoplanets, an achievement that could revolutionize our understanding of the universe. In addition, the super-powerful telescope has also made other notable discoveries. Astronomers using the James Webb Space Telescope have found complex organic molecules similar to a kind of smoke or smog in a distant galaxy. This finding represents the earliest known example of complex organic molecules in the universe detected by humans. Personally, I find it astonishing and at the same time disturbing that these findings in the far reaches of the universe are transforming the foundations of our cosmology. This discovery is truly shocking, and here's the reason for its importance. First, these chemicals, technically called aromatic hydrocarbons, have been identified in a galaxy that formed when the universe was about 10% of its present age. These carbon-based molecules are found in petroleum and coal deposits on Earth, as well as in atmospheric pollution such as smog. What makes this discovery especially intriguing is that the molecules found are not simple like water or carbon dioxide, but are large, complex molecules with dozens or even hundreds of atoms in their structure. It is amazing that the universe was able to create such large and complex molecules so quickly after the Big Bang, which defied expectations based on our cosmological models. To put it in perspective, the light that astronomers detected from this early galaxy began its journey less than 1.5 billion years after the Big Bang, whereas the universe is approximately 13.8 billion years old today. That means that we are observing the first steps in the formation of the universe as we know it today. What is most impressive is that this detection is due to the Webb telescope, which will allow us to make observations of this type for almost 1 billion more years. If we could look even further back in time, would it be possible to find more of these molecules even much closer to the Big Bang? This raises fundamental questions about our science and our cosmological model. Until now, previous efforts to detect complex organic molecules in ancient galaxies could only tell us whether or not the chemicals were present. However, with Webb's ability to provide higher resolution, we can now see the real details of where these molecules are found. Furthermore, the non-uniform presence of these molecules in the early galaxy SPT 041847 has yet to be fully explained. However, what is truly impressive is that this galaxy was already just as massive as our own, and its stars have generated as much carbon and oxygen as the stars of our Milky Way, despite being only 1/10 the age of our galaxy. As humanity ventures into the unknown, armed with knowledge and a deep seed of understanding, we are humbled by the vastness and complexity of the cosmos. With each scientific breakthrough, we move one step closer to unraveling the mysteries hidden among the stars. As our cosmic exploration network works, it is only a matter of time before the universe reveals new secrets. As scientists analyze the atmospheric composition of K2-18b and other exoplanets like it, they are beginning to ask deeper, more fundamental questions about the origin and distribution of life in the universe. Could these planets, with their hydrogen-rich atmospheres and potential subsurface oceans, serve as incubators for microbial life or even more complex organisms? The presence of carbon-bearing molecules is an encouraging sign, but it is only the beginning. Life, at least as we understand it from our experience on Earth, requires not only water and carbon but also the right energy sources, chemical gradients, and long-term environmental stability. One of the remarkable aspects of the James Webb Space Telescope is its ability to probe not just planetary atmospheres, but the very nature of the light emitted, absorbed, and scattered by distant stars, galaxies, and interstellar dust. This enables researchers to gather information across vast stretches of time and space. With each new dataset, the line between known and unknown shifts ever so slightly, allowing scientists to reconstruct cosmic history in ever greater detail. Every molecule detected in an exoplanet's atmosphere, every trace gas, every subtle fluctuation in starlight, these are the clues in a universal puzzle that spans billions of years. For K2-18b, future observations are expected to focus on establishing the consistency and distribution of atmospheric molecules across multiple transits. Repeating the detection of dimethyl sulfide or other potential biosignature gases would represent a landmark moment in the field of astrobiology. But scientists remain cautious. Many naturally occurring processes, such as volcanism or photochemical reactions, can mimic the same spectral fingerprints as those created by life. This is why cross-validation from different instruments and missions, such as the upcoming ESA aerial telescope or ground-based observatories, is essential. Even as Webb turns its attention to exoplanets, it continues to unravel mysteries on galactic scales. The discovery of aromatic hydrocarbons in an early galaxy not only challenges our models of chemical evolution, but also raises intriguing questions about the timeline of organic complexity in the universe. How could such sophisticated molecules form in environments that are, in cosmic terms, barely out of their infancy? The early universe was once thought to be a chaotic, hostile place, filled with ionizing radiation, violent supernovae, and sparse elements. Yet now, evidence suggests it was also a place where organic chemistry was already thriving. This implies that the building blocks of life may have been present much earlier than previously believed. If planets with carbon-rich atmospheres existed billions of years ago and harbored oceans or other life-supporting conditions, then life could have had a much longer head start than we imagined. It shifts the narrative from "are we alone?" to "how long have others possibly been out there?" It redefines our search from looking forward into future colonization to looking backward into an ancient biological heritage we might share. There are also philosophical implications. Humanity, equipped with instruments like the Webb telescope, is now peering into epochs of cosmic history that were once the domain of myth and speculation. What we are uncovering is a universe teeming with complexity, mystery, and potential. From the molecular smog of distant galaxies to the reflective clouds of alien worlds, each discovery tells us that nature is more inventive and prolific than we dared to dream. We are not just observers of the cosmos, we are its children, born from the same processes we now study. K218b has become more than just another exoplanet. It is a symbol of a new frontier, one that does not exist in science fiction, but in peer-reviewed journals and data streams from deep space. It invites a new generation of thinkers to redefine what it means to live in a universe that might be biologically active, even fertile, in ways still unimaginable. In the coming years, technological advancements will further amplify our capabilities. The Roman Space Telescope, launching later this decade, will complement Webb's narrow-field precision with wide-field surveys. Together, they will create a holistic picture of cosmic environments from the smallest planetary atmospheres to the grandest galactic structures. Interdisciplinary teams combining astronomy, biology, geology, and chemistry will forge new paths of inquiry, transforming our understanding of habitability from a terrestrial